Okay, dear esteemed colleagues and friends, I'll try to show you in this talk how, what is this? Yes. How physics can contribute to the third of the 17 Sustainable Development Goals of the United Nations. Physics and medicine, for a long time, belong to two different worlds. Physics was a science, and for a long time, medicine was an art. And if, at least in my view, it should continue to remain an art up to some extent, the discovery of the properties of ionization radiation has seeded a strong connection between physics and medicine. And this has legitimated the concept of life science, which has been supported also by the progress of genetics. Imaging has been the key in the 21st century. And this is, for me, the best example, imaging, of the strong connection between physics and medicine. And medical imaging is, as Elias Zeoni said already 10 years ago, is a model for the style of interdisciplinary science. And he insisted during all his mandate on the fact that medical imaging should be supported because it will be a real landmark, I would say, for the 21st century. Imaging is also at the heart of interdisciplinary science for, as you said here, generating and using spatially and temporally resolve biological information. And this combination of technological innovation and biological understanding is now even more at the forefront of what drives the scientific changes. And you just have to look at all the progress which have been made in a number of emerging technologies. Whether it is related to nanotechnologies, to quantum concepts, artificial intelligences, and all these things contribute a lot, even today, to the development of medical imaging. You certainly remember that the first Nobel Prize in Physics was given to Röntgen in 1901 for the discovery of the X-rays. The X-rays at that time were considered as very, very fundamental particle, and so it was a very fundamental particle, as fundamental as the Higgs boson, which has been discovered 10 years ago. But Röntgen has a fantastic intuition, only 2 weeks after his discovery, to take this picture of the bones of his wife's hand. And to my knowledge, this is the fastest technology transfer example. And with huge social implication and medical implication, if you consider that today more than 500 million X-ray exams are performed every year in the world. A second interesting example is the development of the tomographic principle, again by two physicists, MacLeod and Hounsfield. And they got for this the Nobel Prize in 1979. As most of the imaging modalities today are using the tomographic principle, perhaps it's not bad to quickly explain for those of you who don't know how it works and what it really means. If you take an object, you illuminate it on one side, and you project what you see on the screen on the other side. Here I have taken only 2 points for simplicity. So these 2 points are defined in the projection by 2 coordinates in a plane where the projection is made. Now if you rotate the source and the detector around the patient, it's easy to see that each of these points will describe a sinusoid in the plane coordinate angle. And if you take the projection of all the points, you produce what is called a sinogram. And this sinogram is nothing but the Fourier transform of the real distribution of the point in 3D, 3 dimension, in the patient's body. So when you have the sinogram, you just have to apply an inverse Fourier transform and get back to the real distribution of the points that you have been observing in the human body. MRI, I also strongly benefited from the work of physicists, and not less than 4 Nobel Prizes have been given to physicists for their work on MRI. 2 in 1952, to Felix Bloch, who, by the way, has been also the first Director General of CERN, so a center where we are doing very, very fundamental physics and a priori far away from medical considerations. And Purcell was a physicist at Harvard. And later, in 2003, Sir Peter Mansfield and Paul Lauterbach, who actually was not a physicist but a chemist, and they got also the Nobel Prize in physiology in medicine, in this case, for their work on MRI. Georges Charpak, a physicist at CERN, has developed the multi-wire proportional chambers, for which he got the Nobel Prize in 1992, and which offer a fantastic possibility for digital radiography at very low doses for the patient, and also for the medical doctors around, by the way. So the general trend today is to go from the anatomical imaging, which has been actually the start of the imaging processes in medicine, to functional imaging, and eventually to what is called molecular imaging. For anatomical imaging, the fundamental modalities are typically the X-rays, of course. Ultrasound, I forgot to say here also MRI. MRI provides a very, very precise anatomic information in the body. If we want to go to functional imaging, in fact, to see how the organ is functioning, you can use also MRI in the so-called bold modes. So basically, this mode of MRI measures the blood flow in certain part of your body. And as the blood is the vehicle of energy, and this is particularly important in the brain, for instance, if you have a part of the brain which is solicited by something, then it will have to work, and then it will require energy. This energy will be taken by blood. So if you measure the blood flow, you will have an information of the part of the brain which has been solicited. US Doppler is the same. When you measure the flow of blood in your carotids, that's also functional imaging. It means that something is happening, there is a demand of blood in your brain. And also in functional imaging, you have the so-called nuclear medicine modalities, those single photon emission tomography and positron emission tomography, which play also an important role. But the ultimate goal is to go to molecular imaging, which is the visual representation, the characterization and quantification. Quantification is an important word here, of biological process at the cellular and even the subcellular level within living organism. And then you can target specific cell receptors that are either overexpressed or underexpressed when you have a disease, certain disease. You can, very important, diagnose a disease in its very early stage and ultimately before it becomes symptomatic. That, I would say that would be the Graal. This is the Graal. So to make an exam, to see, oh, you have something wrong here, you still feel in a perfect condition, but something is becoming wrong. And in 1, 2 years, 10 years from now, you will have a real problem. And that opens the way to what is called personalized or precision medicine, depending on the country where you are mentioning this notion. And what is personalized medicine? Is to apply the right treatment to the right person at the right time. So at this stage, I have mentioned molecular imaging is really the domain of positron emission tomography. And perhaps here again, forgive me, but I will just quickly explain how a PET scanner is working. You start from a molecule which is involved in some metabolic process that you want to study in the patient. Typical example, sugar. Sugar, because sugar, again, is related to energy. You know very well that cancer cells develop more rapidly than normal cells. They need more energy. So they need some sugar. They will uptake the sugar if you inject sugar to the patient. But okay, it's fine to inject sugar, but you want to see. And to see that, you label the sugar with a radioactive isotope. And not any one. You choose an isotope which is deficient in neutron, so that one proton in this isotope will transform into a neutron. And as you need to balance the electric charge, it will emit a positive charge, positive particle, which is a positron. What is a positron? It is an anti-electron. This anti-electron will be ejected from this radioisotope, which is, I remind you, attached to the sugar or whatever metabolic molecule that you want to study. And then it will be immediately in your body, but your body is full of electrons, standard electrons, I would say. And when an antiparticle meets a particle, it will immediately annihilate and release its energy, the combined energy of the two, particle and antiparticle, in this case, in 2 gamma rays, which are emitted back to back, more or less aligned, I would say, and going in 2 opposite directions like this. And each gamma ray carries an energy which is equivalent to the mass of 1 electron. When you have understood that, you realize that the first thing to do when you want to look at a patient like this, you inject this molecule to the patient, and then you surround the patient with a ring of detectors to collect these 2 gamma rays in coincidence as many times as necessary to produce an image. And of course, you will do that in different directions. You remember the tomographic principle. And then you will reconstruct a sinogram of this. And as I said, sinogram is nothing but the Fourier transform of the 3D distribution of the radioactivity uptake in the patient. And in the case of cancer, where this, the tracer is a sugar labeled with, very often this is fluorine 18, this positron emitter, you will see an image of the tumors and the metastases. And you apply this inverse Fourier transform or some other reconstruction method which are now more elaborate than that, or faster to put in operation. And this is what you get, an image of the patient with the black point representing, for this poor patient, a number of not so nice things, I must say. Okay. Oh. I did not want to go that way. I went back here. I should have moved forward. Okay. Now it's really... Okay. A few years later, that's an interesting story. One of our colleagues at CERN, Dave Townsend, was a physicist. He was working in close connection with Professor Donat at the Geneva Cantonal Hospital. And they asked for a grant at the National Swiss Foundation to build a prototype PET scanner. Unfortunately, they did not have enough money to build a full ring of detectors. So the only thing that they could do is 2 partial rings. I don't know if you can see, yes, 2 partial rings like this, and 2 holes were remaining. And Dave Townsend has the brilliant idea to say, well, let's fill these 2 holes, on one side with an X-ray source, on the other side with an X-ray detector. And then we make all these things turning around the patient in order, again, to have the tomographic principle for both the PET and the X-ray machine. And that was the first time that we could combine an anatomic information provided by the CT and functional or even molecular information provided by the PET. That completely changed the picture and the future of PET imaging. Now you cannot find anymore in any hospital a single PET. You have always a PET CT. And that was considered as the invention of the year by the Time magazine in the year 2000. And that was also breaking the simple rule of arithmetics, because it was really considered that 1 + 1 makes 3 and not 2. I would like to finish my talk. Crazy. I come back to the title, and I would like to mention, to insist on the last word, for everyone. Contribute to good health and well-being for everyone. A few years ago, or quite recently actually, there have been a study by the Lancet Oncology Group focusing on 11 cancers. And they conclude that the mortality in low and medium income countries is much higher than in high income countries. And this is particularly important for young people. And there are many reasons for that, but an important reason is the poor access to imaging tools and delays also in diagnostics. So it makes sense then to push in this direction for the deployment of imaging, modern imaging technology in these countries, not only because it saves lives, but they also demonstrated that it could have a huge economic impact. With a return on investment, we can be very, very significant, particularly in low-income countries. If you look at the distribution of the nuclear medicine, so one of the modalities in nuclear medicine in the world, you see a clear difference between the north and the south. The lighter the color, the less machines are available for the people. So something has to be made in this direction, and I see 3 different levels of action. The first one is to define the most critical medical targets in these countries, and there are many. Some of them are the same as us, for us, some of them are specific for some countries, and this has to be clearly identified. The second point is to develop a training strategy for medical and technical experts. The problem is to run this machine, you need experts, medical experts and technicians, and does not exist in such countries, or very, very little. So this strategy has to be important. Another one is to organize, in collaboration with the PET industry, an efficient maintenance system, because these systems are complex. If a machine doesn't work at some moment, you need to repair it quickly, otherwise it's useless. And this is why myself, but not only myself, because there are many people behind that, we are involved in an initiative which is in preparation by the World Health Organization to push an effort for the deployment, in particular of nuclear medicine technologies in such country. This is also supported by the International Atomic Energy Agency based in Vienna. So the last point, I think this is my last slide, if I can move it. Because physicists, and I will come back to that, we believe that we can not only bring our know-how and experience to improve the performance of the machine, but we should also use this expertise to develop machines which are really important for these categories of people. So basically to develop machines which are more cost-effective, which are portable, because very often in this country the density of population is very low. So you have to bring basically the machine to the people instead of bringing the people to the machine. And there are a number of technologies that I will not describe here in detail, but in particular the very popular at this time, this is time-of-flight technology using, let's say, modern technological development, which can help a lot to reduce the cost, to improve the sensitivity of the machine, and therefore to provide at a lower cost and better efficiency this technology to a larger majority of the people, as is the case today. So, having physicists and physicians working together makes sense. Thank you very much.
We have time for one question. João?
Yes, you did mention, maybe I missed it, anything about artificial intelligence in connection with imaging?
Yeah, artificial intelligence. Perhaps I will go to the microphone. Yes, I have quickly mentioned that artificial intelligence is one of these emerging technologies which can play an important role. There are many, but this one in particular is very popular at this moment, and it's used. These machines are complex, so you produce signal, electronic signal, which need to be analyzed, and then they need to be filtered, and then to be used for image reconstruction. So what I have shown today, so at the end, what counts for the medical doctor is to see the patient, or to see through the patient, non-invasively. So, and at all this level, artificial intelligence already provide a significant improvement and is likely to provide much more in the coming years.
Yeah, I would like to confirm that, for instance, in the field of rare disease, where diagnostic is a real problem because we have 8,000 rare diseases, and it's quite difficult for the physician to identify this disease. Now we tend to rely on imaging and artificial intelligence in order to be able to identify, to diagnose those diseases where sometimes you have 4 years of people looking for a diagnostic and they don't have a diagnostic. But I would like to tell you that I was personally associated to some research where we identified a radioligand based on tetrabenazine to detect the degeneration of the dopaminergic neuron in Parkinson's disease. And we have shown that it starts 20 years before the appearing of symptoms. And actually this marker exists. It's available on PET, but it's not so much used because even if you detect 20 years before that there is a risk of Parkinson, we don't have any treatment to prevent Parkinson. So it goes along with preventive possibility to have preventive measure. And also the absolute value is something which is sometimes difficult to assess for the risk of a disease. What we need to know is the slope of decrease of the dopaminergic expression into this to substance nigra. So this needs repetitive assessment of the image. So it makes it quite difficult, in fact, to expand it in the population.
Thank you, Daniel.
So it's my pleasure now to welcome Manuel Velarde from the University Complutense in Madrid. He's going to give a talk where electronic electronics meets mechanics at the nano level. Thank you.
Good afternoon, ladies and gentlemen. Thank you, Professor Pombeiro, and thank you, President and the organizers of the meeting. After 40 years working in fluid mechanics and nearly retiring, I thought about what to do next. Well, it was a very optimistic approach. And then it turns out that I came with a crazy idea, and I'm going to talk about this crazy idea that ended up in a patent. So here it is. Wait a moment. So you are familiar with surfing, either near shore or like the Chinese knew about 1,000 years ago near Shanghai. They had the opportunity of going upstream, not downstream, with goods and then back to the place of origin. So this is just to tell you that there is some fluid physics of waves which are of some interest. Now what I'm going to do now is to show you that indeed if a person could surf, so an electron in a crystal. Now this is of interest for the younger people because what I had to do when I started working on this near retirement age is to go through the textbooks of solid-state physics because I did not have solid-state physics in my curriculum, in my education. Finally ended up by having a patent, passes in the United Kingdom. I didn't pass through the European Union because it's too much work. In the United Kingdom, it was a question of one overnight document and then I think 100 or so pounds, together with Professor Wilson, Guy Wilson. I'm going to talk about features, the traditional and expected, and the novelty of the approach. This is a transistor in a very elementary way, so you have 3 points which are of interest that aren't necessarily metals at the moment, but I'm going to talk about what happened in the channel. Now, theory, prediction, and implementation, very quickly. Could we move the charge, an electron, without an electric field? Sounds like science fiction. I'm going to prove you that this is real. Oh, sorry. Another moment. Now we have to study the evolution of the atoms of the crystal, of the lattice crystal, the evolution of charges, the electron, and the evolution of the coupling of the two. The atomic crystal is based in textbooks, which I had to learn at the age of 70, based on harmonic oscillations, which is sinusoidal, which is what we call phonons from the quantum way of approach. Quantum mechanically, we have phonons, and from phonons built up the whole electronics. The problem with the harmonic potential is that it can only be used in the neighborhood of the minimum, because it's unphysical, save the very small oscillations around the minimum, and cannot be used to tackle thermal expansion and some of the features of a crystal, of a solid. Now this is a more realistic potential already built in the 1920s at the suggestion of Max Born by Morse, one of his collaborators, and you see that this asymmetric has a possibility of thermal expansion because the midpoint is not in the middle, but rather shifted. Oh, sorry. This is the potential, it's an exponential. It could be Leonard Jones in the usual chemistry literature. We have a couple of 3 parameters. I'm going to skip the detail. Wait a moment. Wait a moment. Here is the potential, also relative to the harmonic potential. You see the asymmetry that permits explaining thermal expansion, which is not possible. Thermal expansion, a very elementary property of a crystal, is not possible to be described with a harmonic oscillator. So you go to the textbooks or solid-state physics and at the moment say, oh, be careful, forget about what we are talking about, we need to go to some extra business and a harmonic interaction. Now, this is a way you can feel what is going on here. Now, if you look for the specific heat of a material, you see that there is a very low temperature, the Debye approach, or the earlier Einstein less realistic approach. When you increase temperature, then you go through the long petit plateau, and then if you focus, wait a moment, sorry, and if you focus on the high temperature limit, then you see that you transfer from the situation that was previously to either breaking or melting. It is on the way to breaking or melting, the solitons, very, very exceptional waves appear in a crystal, if there is any. Oh, wait a moment, this is really, it's a problem, okay. So what we see over here is a, this is, let me see, okay. So what we see over here is that when 2 or 3 atoms get together, very near together, we are talking nanomechanics, there is a huge compression. This is a sound, by the way. It's a longitudinal wave. This longitudinal wave, if it is very special, like it is called a solitary wave, the wave in the tsunami or the wave of the surfing, then there is a high peak because of a strong compression. And this is what happens. If there is a regular harmonic approach, Landau invented in a half-page paper in the 1930s what is called the polaron. So charge or electricity is not carried by the electron. It's carried by the electron and the deformation created in the lattice, in the polarization of the lattice. So you insert an electron and you perturb the crystal, and this perturbation is a self-trapping mechanism. Now what I'm going to talk about is about the same phenomenon, but with a nonlinear lattice, where first I'm going to have the deformation, and next I'm going to add the electron, and I'm going to show you that this mechanism works, and I'm calling this as electron as a generalization of the Landau idea of polaron. So I'm going away from textbooks. Now, what is going on over here? So I have a one line. I'm going to talk about one-dimensional problems. So I have over here a donor and an acceptor. The most elementary chemical reaction is just bringing one electron from point 1 to point 2 and then creating a reaction. That's the Nobel Prize of Rudy Marcus. So by photoexcitation, we can excite both the electron and then the mechanical disturbance, the solitary wave, the wave which is very unusual, like the tsunami or like the surfer wave. Unfortunately, I have to introduce some mathematics, but very quickly. So I need to explain, to talk about the evolution of the lattice, of the crystal, the evolution of the electron, and the evolution of the coupling of the two. The evolution of the lattice is classical. It's Hamiltonian approach and Newton's equation. Easy. You learn that in school. The evolution of the electron is also learned in school because it's a Schrödinger equation which is about an electron but probability density. An electron is not a particle, it's a probability density. So I'm going to show you what happens when you apply the Schrödinger equation. And then the coupling of the two have been done by a number of people, starting with Landau. Wait a moment. So the traveling solitron exists before I add the electron. This is what is different from the Landau approach. The nanosoliton is a local lattice mechanical disturbance, only a few units, a few atomic units, with a strong character. Adding the charge indeed also perturbs the lattice, but to a minor way relative to the perturbance of radio. Now this is the solitron. So I have a lattice of 100 units, a crystal, and time is on the right line, 100 time units, make dimensions less. You see, you create a disturbance, and it remains exactly the same forever. This is what characterizes a solitary wave relative to a normal wave. A sinusoidal wave is destroyed quickly. Linear waves, all linear waves are easily destroyed by interaction with solid or with, well, as it is said, with phonons. Over here, a solitary wave is permanent in the form, is not destroyed at all. Now, the Schrödinger equation. If I localize an electron in the middle of the lattice as 200, side 200, then I have localization. But when the Schrödinger equation is applied, immediately the electron goes everywhere. The electron goes everywhere in probability. Don't forget about that. Because people misunderstand quantum mechanics by believing there's a particle in many places. No, no, no. It's probability density. Like in the lottery. In the lottery for 100,000 units is 1 divided by 100,000, each one of the elements. This is the localization of Schrödinger equation. However, if I connect the two, what I have done in the equation before, then what happens is the soliton traps the electron. For instance, if I place a site 200 in the crystal, in the 400 unit crystal, the electron and the soliton, they get together. And this is because of periodic boundary condition I see going back and forth. If I place the electron at site 200, red, and I place the disturbance of the lattice at 400, after some time the soliton binds, the wave binds the electron and creates the solitron, which is a generalization of the polaron concept of Landau. Here it is, an experiment with polydiacetylene based on the theory developed. So I may start with two initial excitations which are supersonic. One characteristic of the solitary wave is that it is supersonic. Supersonic on supercritical in water. So it was faster than sound, normal sound. However, because of the interaction, after some time, this excitation decays to either less supersonic or even subsonic, because of the interaction with the electron. But there is something interesting, is that if I apply an electric field, I could get transfer of the compound electron and soliton. But I also could have the possibility of the field not affecting the transfer of the electron bound to the soliton. You see a flat line, 4 orders of magnitude in polydiacetylene, from 10 to the 2 volt per meter to 10 to the 6 volt per meter in polydiacetylene, which is a polymer not of the class of the Nobel Prize given to the doped or dopable polymers. No? Polydiacetylene is a perfect crystal, non-dopable. Oh, wait. Here it is, the polymer, the monomer, and the polymer. It is a one-dimensional electronic element, one-dimensional perfect transfer. This is the electron microscope. So, in my approach to the problem, which I call SFET, Solectron Field Effect Transistor, I have to control what is going on when I have the transistor. So here, the threshold voltage, which is important for a functioning of a transistor, can be controlled by the choice of the electron affinity of a layer that I have down the gate. This is not the case for a regular transistor, which is controlled by the doping. There is no doping for polydiacetylene. Gate, source, and drain in the typical transistor. We can use rare earths, of which there was a talk this morning. So, because in order to inject electrons, it's sufficient to have a work function of the metal below the affinity of the polydiacetylene. So, this automatically injects electron and could excite in polydiacetylene even the mechanical disturbance. I can add this M layer before the gate and the channel which is below, which is compound of polydiacetylene. Now this is one of the results, typical results of a field effect transistor. So I have over here the source drain current against source gate voltage. That's very standard. Here it is quite different. If I plot source drain current against source drain voltage, there is no change after I go through VT. You see? For a given gate voltage, the current along the channel is constant, no change, and no need of electric field. So I could move charges without an electric field. So there is no Ohm's law. So there is no Joule heating. So heat is alien. Sustainability might be the name behind. The inverter is easy. My last transparency in a moment. It just put in two of them, and then you have the Boole algebra and the complete transistor, whose patent was granted in 2020. Is polydiacetylene unique? Not at all. Even ultra-pure silicon or any other polymer, any other semiconductor that could be used, having the possibility of sustaining strong compressions, which is following a non-harmonic potential, which is, for instance, the quantum mechanically based Morse potential. Having said that, I finish with the acknowledgement. Here is the bunch of colleagues who more or less helped me going through this crazy idea. Professor Sheberikov, unfortunately, is already passed away. Professor Everin from Berlin. Larisa Brisik from Kiev, still working under the bombs and collaborating with me. Leonor Cruzeiro from Faro. Jean-Pierre Launay from Toulouse, and Professor Guy Wilson from London, with whom I submitted the patent, and I was granted in 2020. Thank you very much for your attention.
Thank you very much. So we have time for one question. Yes.
I hear very badly, so speak loud so that...
Okay, thank you very much for, as you said, crazy ideas, because I believe we have to have a dream to go further in what we are doing. But in your system, in what you are proposing, I think that you know, any carrier, the lifetime is not infinite, it's finite, because you have a disorder, positional disorder. This positional disorder means that you are losing energy. And your model may be only applied on 1D systems, because the figure of merit is the mobility. And if you have some obstacles, the mobility goes down, and then you lose the momentum that you are looking for. How you combine both this? Positional disorder, because order, because you have to assume that you don't have a positional disorder, you have infinite lifetime for your carriers, and the mobility is not disturbed.
You have to be careful about concepts. Mobility is the initial slope of the velocity. 200,000 in regular units. There is not better in the market for PDA, but this is experimentally found. And you have seen that very quickly there is the jump into the frontal line. In second, polydiacetylene is perfect. At the end, there are going to be some defect. But you have plenty of room to see that there is 4 orders of magnitude, 10 to the 2 to 10 to the 6 volt per meter in polydiacetylene. The electron is going unaltered. Certainly, if there is some disorder in another crystal, you may have problems. But the compression of the solidon is so strong in energy. We are talking about infrared versus electron. That's several orders of magnitude. So the solidon is so strong that traps the electron and is the dominant feature. The alteration of the lattice by the injecting of electron is minor relative to the strong character. We are talking about 2 or 3 atoms nearby, half equilibrium distance. Very strong. Okay. The question is that there are not many materials that sustain such compression. So I'm talking about a theoretical prediction. To get a patent, you don't need to have a prototype. It was estimated about 500,000 constructing a prototype, a demonstrator. We didn't have the money. We were theoretical people, and so I got the patent because of feasibility.
Okay, so let's thank Professor Velarde. Thank you very much for this provocative talk.